We're very eager to get the high-resolution gravity map of the moon because we really want to study what the moon is made up on the inside.
With gravity, you can see through matter. In other words, you're not restricted to seeing what's on the surface. You can also see what's inside. And that's really a remarkable property that we can use by mapping the gravity field of the moon.
The first thing we do, actually, once the map is in our hands, is compare it with a topography map, hopefully of comparable resolution. And from there, we can look at specific features, such as mountains and basin craters, and compare the gravity and the topography. This is where it gets really interesting. You would normally think that if there's a mountain present on the planet, there's additional mass and additional gravitational signal as the spacecraft flies over it. But if it does, and there is no additional gravity signal, then something on the inside is going on that is particularly interesting. And that's what we want to know.
The upper 60% is known pretty well because the Apollo astronauts placed seismometers on the moon. And for about a half a dozen years, we got records of moonquakes. As you go deeper, we don't know nearly as much about the size of the core, whether there's an inner core, how big it is. We think there's a mushy zone, but again, how mushy the mushy zone is yet to be determined.
Understanding how the moon has developed would really help us in understanding how the other planets in the inner part of the solar system, the rocky planets, have also developed.
The terrestrial bodies in the inner solar system are the moon and the 4 planets Mercury, Venus, Earth, and Mars. The biggest of those bodies, the Earth and Venus, have surfaces that have evolved completely away from what their original appearance was.
So comparative planetology is a very key aspect of planetary science, and understanding yet one more piece of this puzzle with this very interesting object, our moon, would be a key aspect of this.
Ready to be surprised.
Because the LGRS only measures distance changes, there's no direct way to tell whether those or how much of those distance changes are due to gravity and how much are due to the other forces. The size of changes that we're worried about are micron level. It's 1/1,000,000th of a meter, so that's very tiny. We have a budget of about 15 microns end-to-end across the system of error that we're allowed. And we're very possessive of all of those microns when we distribute them out to the different aspects of the flight system.
The number one non-gravitational force that we're worried about is the solar pressure, the force that results on the spacecraft when the sun shines on it and reflects off of it. And then there's an infrared force that comes because the spacecraft has a different temperature on different faces of the spacecraft, and that warmth of the spacecraft actually radiates in the infrared, and because there's different amounts in different directions, that exerts a force on the spacecraft.
Like all things, when temperature changes, shape tends to change. Things that heat up tend to expand. So we're very sensitive and aware of how the spacecraft thus changes its dimensions as it moves in and out of shadow around the moon.
And then if the spacecraft has something that evaporates, for instance, the evaporating gas will exert some thrust, and all of these affect the orbit.
The scientist and the engineering team spent a lot of time understanding how big these effects are going to be. How big is a solar panel? How reflective is a solar panel? How hot is it going to get? How can we manage the heaters on board the spacecraft? All of these tiny effects, checked and rechecked and managed by the spacecraft team in development and by the operations team to make sure that the science measurement is made as cleanly and reveals the gravity as clearly as we would like.
It's just like football players, hockey players, anyone involved in sports has to practice and do drills. Same thing is going to happen with our operations team. We've got nominal ones planned. This is important to teach the team what happens normally, what to expect just if everything goes well. But we also have anomalous cases where we throw in faults here and there to see how the team responds to make sure that they can recover the spacecraft and the mission timeline.
we are maintaining contact with the DSN as expected throughout the burn.
All right, copy that. Thank you.
At-low, assembly test launch operations. Lockheed Martin is involved in all of our operational readiness tests. I would describe the relationship between JPL and Lockheed as very positive, and we are one team, we really are. The biggest challenge is definitely time crunch. And so some of our tests either get moved to the time we're at the Cape, so they get shifted to the right later, closer to launch, which is a little bit scary. And so that's the most challenging thing, is just dealing with a very volatile schedule and trying to achieve all your goals within a shifting amount of time.
As soon as we launch, the Deep Space Network is training their antennas up on our spacecraft and receiving Doppler data. The navigators, the orbit determination engineers, will then compute a very precise trajectory that we're on. Then we have another group of navigators called maneuver analysts that then take that trajectory and compute we call it the delta V. It's the change in velocity that we need to get us precisely on the trajectory to the moon. And the spacecraft team then has to take that. These are the people in Denver. They take that magnitude and direction, and they have to determine the turns that the spacecraft makes to point the rocket engine in that direction. Once they do that, they give those turns back to the navigators, who then check the turns to make sure that they are in fact turning to the direction to give us the right delta V, the right impulse to correct the trajectory. The mission planning and sequence team, along with the spacecraft team, will have built the commands that go to the spacecraft that tell it to do this turn and to turn on the rocket engine at a particular time and burn for a certain duration. And so those commands have to be checked thoroughly. At Lockheed Martin in Denver, we have a simulator that we run the commands through. Once I've been assured that the tests have been completed on the simulator and that everything looked fine, then I give the final go that we're ready to send the commands to the spacecraft.
The GRAIL spacecraft are extremely rugged, and that comes from a couple of reasons. One is they're quite small, and there's not a lot of excess volume inside.
They're a little bigger than a washing machine, basically. It's kind of the same size and shape.
Because GRAIL is a mission that will investigate the gravity of the moon, our observable are the gravitational forces acting on the spacecraft. As a result, any forces we consider non-gravitational become a problem, so we need to minimize those.
You can imagine anything that moves, anything that can change, causes perturbations to the collection of the science data. So we've purposely built these spacecraft to not move.
The joints are all clipped together, they're bonded together where appropriate, and produces a small, very structurally sound and very low coefficient of thermal expansion. The GRAIL mission is happening at the right time, at least from a component standpoint and from an infrastructure standpoint.
Every satellite that we've ever designed, ever sent into space, we've learned from those satellites, how cold is it going to get, how warm is it going to get, for how long, do our components work properly in the vacuum of space, are they going to be able to survive launch? We've essentially stood on the shoulders of our predecessors to basically use component heritage that's still recent enough that it's usable and applicable for a space mission.
Anytime you can use components from a previous mission that have been tested and proven, it reduces risk and helps your program be successful.
The spacecraft itself is a single string mission, which basically means that it doesn't have redundant components. Many of the NASA missions have fully redundant subsystems and systems so that if a component suffers a failure, you swap to the redundant unit.
From the inception of the GRAIL mission, we've decided that it was acceptable to use single-string components for two reasons. One is the short duration of the mission, and secondly is the high heritage of these components, which have actually flown in deep space and in much harsher environment than the moon.
The computers and avionics on board are part of what we call the command and data handling subsystem, and that is heritage from Mars Reconnaissance Orbiter, also known as MRO.
What we've done is we've packaged several boxes, several components from MRO into a single avionics unit.
The solar cells and the batteries used on the GRAIL spacecraft are the same model as were used on the Phoenix Mars lander. And since they survived the harsh environment on the Martian surface, we knew they'd be more than adequate for use on GRAIL.
We have a telecommunications subsystem. What that is basically the two-way radio. What we've done is used a Genesis derivative for the transponder and for the antennas.
By learning from all the past missions, we can incorporate all that information into our new mission and make sure that our mission goes off successfully.
Because the lunar environment is a lot more benign than Mars, then components that have flown and functioned successfully on Martian missions give us very high confidence that they will perform well for GRAIL.